Hello, beautiful people. Welcome back to our lecture today. And this is the final topic of our semester. So, yay! So, in this lecture, we will discuss about we discuss the active filter. So first, let's compare the between active and passive filter. Passive filter are those without any active component. So RC network are a good example. So we can have an RC network connecting this configuration, and it will act as a band pass filter. A high pass filter. Whereas if you connect the signal and couple a capacitor from the output to the ground in this RC network, you can have it acting as a low pass filter. So active filter means there are one or more than one active component. So op-amp is an example of active component. So this is a high pass filter with a voltage follower, which is an op-amp, and this is a low pass filter with a voltage follower. So technically, it's just the simple RC high pass network connected to a voltage follower. So why do we need to use active filter? So there are two main reasons. The first reason is the maximum gain or maximum value of the transfer function can be larger than 1. The second or the biggest reason is that the loading effect is actually minimal when you use active filter. So the output response of the filter is essentially independent of the load driven by the filter. Talking in terms of active network design, there's a few things to be considered. So all of the previous circuits that I show you, like the low pass RC network or the high pass RC network or the low pass high pass RC network with the voltage follower, they are basically a one pole filter or one pole network. So for a one pole network, the slope of magnitude curve outside the pass band area is like plus or minus 20 decibel per decade, and this characteristic is called roll-off. Roll-off is going to become sharper and steeper if you're adding more pole to the system. That means for a higher order filter, and it's usually it will have basically a steeper rolled up. So let's say 2 pole you're gonna have 40 dp, 3 pole you have 60 dp, and this is usually one of the specification that is given for an active filter. Finally, beside low pass and high pass, you can actually have different type of filter design. This one right here is an ideal characteristic for band pass filter, and this is called a band reject. So of course, usually you know that the slope is, if you have only one pole, is 20 dB per decade, right? So you can actually add more pole to the system to make the slope steeper and steeper. So general two-pole active filter. Let's start considering this general filter in here. We have a voltage follower with some general admittance, and we're gonna mark that from Y1 to Y2, Y3, and Y4. Okay, Y1 and Y2 are leading from the input to the positive terminal of the voltage follower. Y3 is the feedback from the output back to the middle, like the node between Y1 and Y2. Y4 is basically between the positive terminal of the voltage follower and the ground. First, we need to derive the general expression for the transfer function Ts, which is equal to output over input in terms of the general admittance y1 to y4. So first, let's consider the node VA using Kirchhoff current law. So we're gonna have this current going in this direction equal to this current plus this current. So we're gonna have this equation here. Next, you apply KCL for this node. Likewise, you're gonna have VA minus VB y2 equal to VB multiplied y4. So due to the characteristic of the follower, you're gonna have VO is gonna be equal to VB. So this is basically that's how the voltage follower work. It transfers the voltage at the input here to the output, and should be equal. And because of that, you can actually set VA, which is going to be equal to VB multiplied by y2 plus y4 over y2, and VB equal to VO, the output. So you substitute that in here. Okay, let's move on quickly. So if you use this equation, you can substitute in for VA and VB, right? So that you can basically make this whole equation in terms of only VI and VO. So I did that in here. Finally, I can multiply both terms for both sides for y2. I'm gonna have my equation to this, distributing everything in. Now I realize I can cancel something from both sides, so I cancel this and this. I cancel this term and this term because it looks similar on both sides. So now I'm left over with the rest, and I can basically derive my VO over VI, and I have this expression. Okay, now we need to consider a two-pole low-pass Butterworth filter. So in previous slide, we derived the general expression for VO over VI in terms of all of the general admittance. So to obtain a low-pass filter, both Y1 and Y2 need to be a conductance, allowing the signal to pass into the voltage follower. Y4 need to be capacitor. Y4 need to be capacitor for the output to roll up at high frequency. Then the high pole function will need Y3 also becoming a capacitor. So now I replace this Y1 with a G1 conductance, when conductance also is like inverse of resistance, so you can have G1 equal 1 over R1, G2 equal 1 over R2. Put in the Y4 capacitor for Y4. I have this to be SC4, and the admittance in here will be SC3. Remember, admittance is inverse of impedance. So now I substitute all of the actual component in. I can have 2 resistor in here and 2 capacitor. So just a reminder, so this is for low pass. So when we get to the high pass example, you actually just have to flip the position of the capacitor and the resistor. So now we can have this form of the transfer function. So when omega equals 0, so S will be equal to 0, right? You're gonna have the transfer function will be equal to 1. When omega go to infinity, this will become very large. So this whole fraction go to 0. That's why it's a low pass filter. The Butterworth filter is often called the maximally flat magnitude filter, and it's called maximally flat because it's basically the filter is as flat as possible within the bandpass region. So this can be achieved by technically taking the derivative of Ts, then set as many as possible equal to 0 at the center of the bandpass. Okay, that means we only need to consider at 0 frequency omega equals 0 for the low pass filter, and we also need to set only one. So let's move on. So if I assume that G1 and G2 are the same and it's both equal to G, so let's say it's both equal to R, I set both resistance of R1 and R2 are equal to R. I can write my expression like this, right? So I can simplify it. I can write this term as tau 3 and this term as tau 4. Now I can write my transfer function in terms of omega and tau. I can basically multiply this together, fractioning out like a real part and imaginary part in here. Then I can write my magnitude of the transfer function in this form. So now we know that maximally flat filter is defined by setting derivative of transferring function at 0 frequency to 0. That means this. So first we need to find what is the derivative of this. So we try to derive in terms of omega. We have this form in here. We substitute in omega equals 0. We are left with this equation. Simplify it, set the whole thing equal to 0, and so from this equation we can see that in order for this to be satisfied, 2 tau 4 have to be equal to tau 3. That means C3 need to be equal to 2 times C4, and because of that we can rewrite the magnitude of the transfer function again in terms of again it's going to be equal to 1 over 1 plus 4 omega tau 4 to the 4, then square root the whole bottom. Anyway, let's move on quickly so we can get to the important part. The corner frequency occurs when this whole number becomes 1 over square root of 2, or this whole 4 times omega 3 dB multiplied by tau 4 to the 4 equal 1. So now we can write our expression of 3dP corner frequency, 3dP frequency to be 1 over square root of tau 4, and that is equal to 1 over square root of 2 multiplied by tau 4, and that's equal to 1 over square root of 2 multiplied by R C4. Generally, we can actually write it simpler as omega 3dP equal to 1 RC. If we use this equation and this equation together, we can have C4 is going to be equal to 0.707 of C, and C3 is going to be 0.141 of C. So now we actually can simplify the expression like this, the circuit like this. So I can give you a what's that called, the circuit of the two-pole low-pass butterworth filter. Okay, since it's at two-pole, the slope after the corner frequency is going to be negative 40 dP per decade, and we previously derived an expression for the gain, the magnitude of transfer function to be this, right? We can write it in another form, and let's accept this as the final form to be 1 over square root of 1 plus f over f 3dP, which is the 3dP frequency, then to the fourth. Okay, Now we are considering the high pass Butterworth filter. This one is even easier. So since, as I said before, what you can do is you can just basically flip the R and the C position of R and C. So now you can have, this is the circuit for your high pass Butterworth filter with 2 pole, and as you can see here, the slope is 40 dp per decade. You flip the position of F and F3 dp to get your equation for the magnitude of the transfer function. Okay, what if I have more than just 2 pole? So in general, you can have an expression of the transfer function magnitude, and you can write it down in terms of this equation and this equation. This is for the low pass K and this is for the high pass K. Substituting n for the number of pole, or the order number that you have in your circuit. So here is one example for the 3 pole low pass filter. Here is one example for the 4 pole low pass filter. Here is for the 3 pole high pass, and here for the 4 pole high pass. Alright, that's it for today. I hope you guys learned something new. Our final lecture will be on design application of an active high pass filter. So I'll see you guys next time. Bye.